We're continuing with section 2.3 on elliptic curve cryptography. It begins by asking what are elliptic curves. If we consider for that purpose a finite field f sub q, where q is a prime number greater than 3, and in the cryptography we're about to consider q will be a prime number much greater than 3. But regardless, if we're looking at that field, we consider it to be the integers that counting up from 0 that has q elements. So in other words, all integers that involve the range of 0 to q minus 1. And we note that all the addition, multiplication, negation that we're going to be calculating on that field are performed using modular arithmetic, specifically calculated mod q. This just being a callback to the previous section. This next paragraph sort of does a quick review of that if you'd like to read it. But if we're considering an elliptic curve, and a lot of these will come with a set of constants or constant values that'll be provided with these coefficients, in this case a and b, we can use that along with a formula to calculate all of the points that will have the familiar coordinates x and y. So if we consider this first example, this is a Weierstrass equation given y squared equals x cubed plus ax plus b, where all of those elements a, b, x, and y exist on the field that we've defined within that range. Obviously, if we're doing mod q on everything, then that should be the case. So there you have it. In the case of Monero, we use a special curve that is a twisted Edwards curve. Again, similarly, where we have this set of constants or these values that we'll be using. So for a given a and d pair, we calculate our x and y coordinates on the equation a times x squared plus y squared equals 1 plus d times x squared y squared. And again, all those values, a, d, x, and y, are going to exist on the field that we have defined. So Monero uses like we mentioned, twisted Edwards curve. It is preferred because it is faster as a bottom line. It's noted here that it requires fewer arithmetic operations in order to do a lot of the sort of just standard cryptographic manipulations that we're concerned with. I think it's worth kind of hammering this point home. So very quickly, let's go to reference 40. We'll pull that up here. And if we go to PDF page 11, you get a couple of the different algorithms that you can use involving different curves. So it's worthwhile just to note these first two, projective and Jacobian. If you look here, this is the Weierstrass curve that was just considered in 0 to Monero. And against that, we can see here we have Edwards at the bottom. Now, this isn't the twisted Edwards curve. The twist is actually the a term that you would multiply the x squared by. But Edwards and twisted Edwards are very close, and we'll see that here momentarily. But as a bottom line, here are all these different approaches. You have Edwards in this list, and if we go down to these comparison charts, notice that the faster techniques, or the ones which require fewer operations, are here at the bottom of each chart. And as we go through the charts, Edwards is at the absolute bottom here, it's at the absolute bottom here, absolute bottom here, next to bottom here, and absolute bottom here. So consistently across these different metrics, Edwards it proves to be very fast. And for the sake of just driving home that the twisted Edwards curve provides, an equivalent result, if we go to reference 38 and pull up page 14, we get this comparison chart between the various forms of Edwards curves, Edwards, twisted Edwards, the rest of it. And you can see that the difference between twisted Edwards and Edwards is just this one extra, what's listed as a D term, this extra coefficient manipulation, where you're multiplying by a and d, or you have to multiply by a in this case of doubling, versus the standard Edwards. Otherwise, extremely similar. It's essentially the same, just with that one little extra tack at the end. So you get similar results versus those other techniques. So here we start to get into the actual points and their manipulation, but before we do that, I had previously skipped over the notes about notation. So if we go back to the start of chapter 2, I think it's helpful just to sort of define the standards that we'll be using as we go through this. So just cutting to the quick with it, lowercase letters are used to denote simple values, integers, strings, etc. And uppercase letters are used to denote more complicated ideas. Specifically, curve points is going to be the really common thing that you see here. So in an easy example, the generator point that we use is going to be denoted by an uppercase G. The order is going to be represented by a lowercase l. That's because that L is just a simple straight up value. And then you have the example of a private and public key pair denoted by lowercase k for the private key and uppercase K for the public key, because the private key is a straight value, the public key is actually a point, and therefore represented, or is a curve point that therefore represented by a capital letter. So we have a few notes about justification for the way that things have been set up. You can read that on your own if you care to. One helpful thing to note is that curve points, you would think that you would always represent a point as the pair of coordinates x and y, but it is easier, or rather there's a technique to just represent elliptic curve points by a single coordinate using a technique called point compression, which we'll go into a little later here. But yeah, you can just represent that point only using one coordinate. It's not really important to worry about this, and they say so here. It's in terms of the conceptual approach where we're just sort of setting up these systems, seeing how they behave. It doesn't really matter if you are thinking about whether you'd use point compression or not, but they implicitly assume it most of the time. So just an important thing to keep in mind. In addition to that, there's a discussion here about cryptographic hash functions. It's worth noting that typically Monero uses Keccak, or a Keccak variant, they say, in order to hash things, but it doesn't really matter. And unless they explicitly say, hey, we're using this hash function for this technique, it's not important. We can just sort of substitute a different one in if we're trying to set up examples or understand everything. If you're unfamiliar with cryptographic hash functions, which it mentions here that they'll just refer to it as hash functions or hashes throughout the text. This is a function that takes as an input some message m, which can have an arbitrary length, and it returns as its output a hash h, also known as a message digest, which has a fixed length, and that hash is going to be some value on a massive range, and every single output that's possible is essentially equally probable given a randomized input. So this has a couple of advantages. They're difficult to reverse, as you'll see many of the cryptographic functions that we're concerned with. They have the property that the calculations are easy to perform given one starting point, but essentially impossible to break if you're starting from another point, or another perspective with a different set of variables declared, or whatever, however you want to say that. But they also have the property where small changes in the message will have dramatic changes in the hash result. So it's if you were trying to find out the content of a message and you just said, oh, okay, well, I'm going to take a bunch of hashes for standard messages and try to target people's message content based on that, hey, here's a payment of X dollars or whatever. It's not going to work to target someone's message that says something very similar by comparing the output, because very small changes in the message are going to have massive changes in the hash. So all of this is just, it contributes to the security of these things, it contributes to their usability. It's important here to note that you can apply a hash function to all sorts of inputs where, you're going to receive an integer, a string, a curve point, a combination of these things. You can use all kinds of inputs to a hash function in order to get a given result or get a given hash representation. And in a similar fashion, you can select or represent the output of a hash in multiple different ways. So that output can just be the straight up numeric, a bit string. You can define that output as a curve point. We'll get that there, but there's that flexibility in terms of the use and the application of those items. So returning now to the section on elliptic curve cryptography, we begin defining these points. So you have point P1, which has its coordinates x and y, and point P2, which has its respective coordinates. And we're declaring that these points are both on the twisted Edwards elliptic curve that we're considering. So henceforth, we're going to shorten that as EC. An additional point can be defined as the sum of those two, and the coordinates of the point P3, which again is P1 plus P2. You use these formulas to manipulate the coordinates, of course using mod q the entire way, and you get the results x3 and y3. So these standard formulas are going to be the basis for point addition and the rest. It's also worthwhile noting that the same thing would apply for point doubling. So if you define P1 and P2 as the exact same point, and you wanted to say, hey, what's the 2 times P1? Well, that's just going to be plugging into this equation the same x1, the same x and y coordinates for both x or point 1 and point 2. So you've got that. If you want to subtract a point, then all you have to do is invert its, it says invert its coordinates over the the y-axis, excuse me, which is just taking the negative x value and then plugging that through, and then you can use this point addition formula with that negative x value. Done deal. And it does mention here that the negative elements, negative x of the field f sub q, are really just negative x mod q, which is to say this result would be q minus x, or, and again, definition from the modular arithmetic section. So whenever we're adding points together, the result P3 that we get as defined by this addition process is going to be a separate point that is on the elliptic curve, which is just to say, hey, it satisfies the equation that we're concerned with, and it exists, its coordinates, x3 and y3 exist on the field that we're concerned with. Now, it's worth noting that every single point in the elliptic curve can generate a subgroup that has, its order or its size, u, that is just essentially a set of other points on the elliptic curve that are multiples of itself. So the example that we're given here is if we consider a point P that has order 5, a subgroup of order 5, I should say, would contain the points 0 through 4P, all the different multiples of P there, so 5 total elements, and every single one of these is a unique point on the elliptic curve. Notice that at 5P, you kind of finish this cycle in the same way of modular arithmetic, where you start back over at sort of the beginning of the group. In the case of the subgroup at 5P, we begin back over at the 0 position and continue on. So in this fashion, this is sort of a cyclic setup, right? If you have 5P plus P, that equals P. In the same way, 10P plus P would equal P. All of this over and over, any multiple of 5 is just sort of a repetition of it. And all of those points in a given elliptic curve can generate, or do generate, I should say, a cyclic subgroup. But the trick here is if a given point generates a subgroup whose order is prime, then all of the points in its subgroup generate that same subgroup. And, the exception being that the 0 point, the point at infinity, anyway. If we look at this first case where we're saying P and has a subgroup of order 5, here are the various points. Well, let's consider what would happen if we take 2P from this subgroup. Well, 2P and multiples of itself, 2P, 4P, 6, 8, 10, so forth and so on. When we're just applying this to this group, what you end up with is 2P, 4P, and then at 6P, you cycle back through and you get to P itself, and then plus 2, you get 3P, and then it cycles to 0. And notice that all of the elements that were in the subgroup of P are also in 2P. Yeah, they're in a different order, but they're all there. And if we oppose that with a subgroup of order 6, which, again, this is a subgroup whose order, is not prime, clearly, and we have these 6 elements, and in this case, now we're going to take 2P from this subgroup, and we just do the straight up multiples, 2, 4, 6, 8, 10. In this case, it just cycles through 2P, 4P, and 0. And it never actually recreates the entirety of the group. You will never get to P, 3P, 5P. It's just these 3 points repeated over and over and over. So in this case, we took a point from the subgroup, and it did not generate, or it does not have the order of the subgroup that we selected it from. In this case, order 3. And that's unideal, as we'll see, or at least for our purposes. So moving to the next paragraph, we define each elliptic curve has an order assigned to it, n, which is just a representation of the total number of points in the curve. So however many points are going to satisfy that function of the elliptic curve function across the field that's defined. That's your order n, and that includes the 0 point, that point in infinity. And we note that the order of all subgroups generated by points are divisors of n. Now, we get a couple of references here as we go through, Lagrange's theorem, and then if we go into this technique down here, Schnoor's algorithm. since they weren't really designated with footnotes or anything, I won't explore it too much farther here. But as a bottom line, if the elliptic curve order, if n is not prime, some points will make subgroups with orders equal to divisors of n. So that's, to my mind, the real takeaway here. And then if you look through this technique, I think it's fairly self-explanatory, or maybe not like this earlier part, but the conclusion, right? You're trying to find the smallest number that if you multiply a given point by, it returns to zero. Which, if you think about it, that's just the smallest sort of cycle that you can complete with p. Any larger value that would return it to zero is just going to be repetitions of this smaller cyclic group. And so you want the smallest possible, and then that will return the order that you're concerned with. So with that, we further note that the elliptic curves selected for cryptography typically have their order equal to h times L, where L is a sufficiently large prime number. In this case, we note, hey, 160 bits sounds reasonable there. And h is a cofactor, which is going to be a very small value, in some cases as small as just 1 or 2. And just for convention, you select a point on the subgroup of size L, and you select that point and you define it as the generator for that given curve. And this is just so everybody has a standardized starting point for how they're going to generate or just handle the mathematics of the curve. And it's worthwhile noting that for every other point that exists in that subgroup, you can get there by multiplying the generator by some value n that is, in the range that we're defining, right, between 0 and L. So all you have to do to get every single point is just multiply the generator by a value. Now I'm going to ask you to be a little skeptical of what I'm saying as we go through the next few paragraphs. I'm pretty sure I got it, but whenever I'm reading through these examples specifically, I kind of get two sensations. One being that the information that's actually being conveyed is pretty straightforward, and the other being that I'm missing something. And in my experience, whenever I get that malaise, it usually means that I'm in trouble. So hopefully that's not the case, but anyway, just keep that in mind for this next little bit. So we're given this example, and I'll just try to state this in my own words, in that, hey, we're going to start at a given point on an elliptic curve, and then we're going to use that point to generate two other points. And we're just going, in order to generate those points, we're just going to multiply this initial point by some numbers. You're just going to pretty much draw those out of a hat, I guess, random numbers, and generate from our initial point p prime a p1 and p2. And in this example, we notice that both of the points that we've generated have order L. And in the case that both of the points that we've generated have order L, it might be interesting to ask, are they, by definition, in the same subgroup with order L? Like, is it possible to have different subgroups with order L? So the first analysis that we're going to try to apply with that is we take both of those points, and we know that if we multiply a point by the order of its subgroup, we get 0. And that, we could kind of return to these early examples that were given. If we have a point P and its subgroup has order 5, here we have its nice little subgroup. Well, 5P is 0 on this, right? We cycle back through. So we imagine doing the same thing with our subgroup of order L, and we can do that for both points. Now, if we consider this equation, that means that we can further rewrite, L times, and P1, keep in mind, P1, like both of these points were just our initial point, P prime, times some number. So we rewrite this equation. We note that, hey, this is congruent to this, which is the same thing as, if we took P prime and we multiplied it by the entire elliptic curve order n, then all of those values are going to return 0. And in this equation, right, if we notice, like, the equivalence of n equals h times L. And so in this case, we have h times L times P prime right here. And in this case, we have, well, n2 times L times P prime, n1 times L times P prime. In these cases, in order for the equivalence to go directly through, we notice that n1 and L2 must be multiples of h. And with that sort of noted, knowing that, in terms of the entire elliptic curve order, there are only, you know, L variations of multiples of H, and that occupies the entirety of the superset, the over the larger group, then that means that only one subgroup of size L is possible, right? So if we start with a point P prime and we generate kind of randomly these two other points, P1 and P2, we notice that both of them have order L, then they must be in the same subgroup, and only one subgroup of size L is possible. So put simply, the subgroup formed by multiples of HP prime always contain points P1 and P2. And furthermore, we note that H times n prime P prime is equal to 0 whenever n prime is a multiple of L, right? In the case where n is equal to H times L and n times P prime equals 0, well, H times L times P prime, just replacing n in that equation with HL, and in this case, recognizing that n prime is a multiple of L, well, that combination is always going to equal 0. And we further note that there are only a number of those variations of n prime that is equal to H, right? So if H is 8, there are H variations of n prime for that, because whenever n prime equals HL, that is when, by definition, this cycles back to 0. Long story short, H times L times P prime equals 0, right? This is the same identity as up here, where n prime is replaced by L. And this identity here is the same thing as n times P prime, because n is equal to HL, and n times P prime equals 0. So this finally concludes by noting that there are H points P in the elliptic curve where H times P will equal 0. If H is equal to 8, then there are 8 points in the elliptic curve where if we multiply them by H, you're going to get a result of 0. And the same argument can be applied to any subgroup of size U. So if we take any 2 points, P1 and P2, and both of them have the order U, we note that, again, those points are in the same subgroup as we discussed earlier, and that subgroup is composed of multiples of n divided by U times P prime. Now, from that, we're given this method to find points in this subgroup that we're considering, the subgroup of order L, and specifically to find non-point at infinity points, right? Non-zero or non-zero points, I guess, in the subgroup of order L. And with this, I believe, if we understand properly, you're given this process where, hey, let's just, find the order of a given elliptic curve, and then we choose our subgroup order that we're interested in and compute the cofactor H by dividing the order of the elliptic curve by the subgroup order. And we just choose any random point on our elliptic curve and we multiply it by the cofactor. And once we've done that, either we will have found a point that is in the subgroup that we're interested in, or we're going to find a point that returns 0, right? In that case, we found one of those point at infinity points, and we just generate another one and go through that process until we get points that are specifically in the subgroup that we're interested in. Now, if I understand this correctly, the test here where we're looking for points that return 0, this should almost never happen, at least in the case of Monero, right? When we're talking about the cofactor, it's noted that typically this is a value that is extremely small. It could be as small as 1 or 2. And remember that there are only H points on the elliptic curve where H times P will equal 0, right? So in this case, if we're saying H is equal to 8, there are only 8 points in the elliptic curve, but a very small value. There might only be 1 or 2. So in the case where we're performing this test and we're interested if P equals 0, then that is an extremely rare case. Most of the time, you're just going to, compute this, and then your P is perfectly fine. It's not going to equal 0. As a matter of fact, you could do this all day, and I doubt you would get that result. So, moving along, we now talk about the scalar product between an integer and a point. So it's just, again, we're representing that here, an integer n and a point capital P. and the scalar product is just n times p. And that computation is very straightforward, right? These are just multiplication of a point. This is repeated additions of that point. We know how to do that. And we get this simple expression where, hey, we're going to find a resulting point that is the multiplication of this integer and this initial point. And it's really easy to multiply n and p2 in this formula, but if we were just given p1 and p2, then trying to reverse that calculation and identify n is, well, as they phrase it here, it's thought to be computationally hard. And they draw this analogy to modular arithmetic, saying that, hey, this is the discrete logarithm problem. And that's extremely common, just fundamental, one of the founding cornerstones of modern cryptography, let's say. And this multiplication that we just discussed, right, where we're going to multiply this point by this scalar value, that's sort of acts as a one-way function in that it's easy to perform in one direction or starting with these values, but if you start without n, it's very difficult to go the other way and calculate n from your output. So that's the founding principle that allows it to be used, that allows rather elliptic curves to be used for cryptography. So again, the scalar product n times p is just repeated to the, it is equivalent to the repeated additions of p to itself, right? Multiplication is just repeated addition. This is the repeated addition of p to itself. And it notes that, in the previous chapter, we had used this double and add and squared multiply approach. We can use a double and add formula that's extremely similar to what we had previously done in order to calculate a given sum, this result r, equal to the scalar product of the integer n and the point p. And so noting again that this plus operation is a little bit non-standard, right? We're not just in order to add up points, this is, in order to add p1 and p2, you had to use this formula to get p3. Well, in this case, when we're doing repeated addition, that's how we're defining those additions. So anyway, with all that said, here's the formula that we're given. We take a given integer value that we're multiplying by, we convert it to binary, and then we use that as instructions for how we're going to either double a sum or manipulate or add to a result the given value. The Python representation that I have for that is right here. This double and add for a scalar product where you feed in the scalar integer and the point p. That should be capital, but anyway. In that case, here we have a nice little bit of code to execute, and we can see that where we're just going to generate a random value, a random integer, I should say, n, and we're going to feed that into the double and add scalar product formula that we have and calculate the answer. And we'll check that against what is just the standard defined scalar times a point operation that is defined in this underlying Python library that I'm using. If that sounds confusing or complicated, don't worry about it. But anyway, I'm going off of the Python library that is built or that is used in the elliptic curve tutorials that were published at this GitHub repository, which, by the way, is an excellent repository. Would definitely recommend somebody going there and toying around with that if you're interested. But anyway, this is just sort of checking that this process that we've written up is actually going to produce the correct result. So let's do that now. And here we have the value that was generated, and here we have the result of using double and add, and then just the standard multiplication that's built into the library. We can see that all of that matches up, so can feel good about that. So with that example finished, we move on to the use of public key cryptography with elliptic curves. Now, in order to do this, we begin with this private key that we choose. This is the lowercase k, and k is just a randomly selected value in the field that we're interested in, right? F sub L, which means it's in the range between 0 and L. And we can use that private key, lowercase k, to calculate the corresponding public key, which is an elliptic curve point, so we get the capital K for that. And it's just in this formula of the private key times the generator point equals the public key, k times g equals k. And this, should look extremely familiar to the NP1 equals P2 or NP2 equals P1, I guess, that we had up here, right? It's just scalar multiplication and the result, and scalar multiplication and the result. Now, we note that, the discrete logarithm problem protects the knowledge of the private key, even though you hand out the public key to the entire world. So someone can go through the rest of, the public key cryptography with this key pair where you have a private key and a public key, and just use those values and know that they are secure. And quick example, I guess, in Python. Let's just generate up, I guess. Here's a simple representation of it. We're just going to take our private key and we're going to generate some random scalar scalar value that's in the range that we're interested in. And then from that, we just multiply that by the generator point to get our public key. And we're going to print out the y coordinate of that public key to see what it looks like. And here's the output of it. You just see that singular value, but there it is. So with that, we move on to Diffie-Hellman key exchange, and this is essentially, just to read it directly, a basic Diffie-Hellman exchange of a shared secret between two people, we're going to call them Alice and Bob, can take place in the following manner. And essentially what happens is both Alice and Bob have their public-private key pairs, and each of them publishes their public keys and keeps the knowledge of the private key only for themselves. So this is just sort of the standard setup that you would expect someone to do with their own private public keys. Now what's interesting is that Alice can take Bob's public key and her own private key and multiply them together. And when she does that, she actually gets the same thing that Bob would get if Bob takes his private key and multiplies it by Alice's public key. So obviously they know their own private keys. They can take the knowledge of each other's public keys and come up with this other value. And the reason why that calculation is the same is obviously, if we look at here this case, Alice's public key times Alice's private key, times Bob's public key. And in order when Bob calculated his public key, he took his private key times the generator. So you end up with this being equivalent to the expression of Alice's private key times Bob's private key times the generator. And in the same way, Bob, from this starting point, he's using his private key and appending it onto this expression from Alice, which used her private key and the generator. So these expressions end up being equivalent. And they can each perform these calculations now. They can each come up with this shared secret and then use that. For example, we're given this case where Alice has a given message M to send, and she could go ahead and hash that shared secret, use that hash to manipulate the message into some value X, right? We take the message, we add in this hash of the shared secret, come up with X, and then send X to Bob. And an external observer who does not have that shared secret is just going to get this value X that they're not really sure how they're going to manipulate it. But in Bob's case, he can compute that same hash off of that same shared secret that, again, he can calculate. Only he and Alice can calculate. And then he can remove that hash from this X that was transmitted and recover the message. So with that, we just kind of conclude by noting, an external observer is not going to be able to manipulate that shared secret because they don't have knowledge of the shared secret. This is the Diffie-Hellman problem. And which is just, again, you're not going to, with only the public keys published, you're not going to be able to calculate that shared secret. And then the discrete logarithm problem, as per usual, protects the private keys from being exposed just because there's knowledge of the public keys, right? So good there. Moving now on to Schnoor signatures. I should actually include this. I did write up these examples, right? So let's just do it really quick. So here's an example. I'm just setting these to hard-coded values where Alice's private key is going to be 867, Bob's private key is going to be and they both calculate their public keys by multiplying their private keys by G. Now, in order to calculate their shared secret, Alice is going to take her private key and multiply it by Bob's public key. Bob, in turn, is going to calculate the shared secret by taking Alice's public key and multiplying it by his own private key. And then if that shared secret that they each calculated, if those are equivalent, then, we can confirm that this product was successful. And in fact, when you run this, we just get a nice little prompt, Diffie-Hellman success. If you want to print up the values, then you can do that quite easily. So there we have it. Moving to Schnoor signatures, we see this is a interactive authentication protocol published by this gentleman, and this allows you to prove, or rather, it allows someone to prove that they know the private key K of a given public key without revealing any information about that private key. And in order to do so, we're given this method that just goes like so. You have the person who wants to prove that they know a private key, and so that person is going to generate a random integer alpha that exists in the field that we specified, right, z sub l. They're going to use that random integer and multiply it with the generator point to compute another point, so alpha g, and they're going to send alpha g off to someone who's going to verify their knowledge. The verifier then generates their own random value, and it's going to be a challenge C, which again, this exists on the field we're concerned with, and in turn sends C back to the prover. The prover then computes their response, R, which is just alpha plus the challenge times the private key, and sends R to the verifier. So now the verifier has everything that they need to compute this response point, which is just the response they've just received times the generator, and R prime, which is going to be alpha g, which they received initially, plus the challenge times the public key. And they just check the equivalence. Does R, this term, equal R prime? So we note that the verifier can compute this value, R prime, before the prover. And so whenever they send this challenge, right, they're saying, hey, I challenge you to essentially respond with the discrete logarithm of R prime. And the only way that the prover would be able to do that is effectively if they have knowledge of that private key. So, yeah, there you go. And it is noted here, except with negligible probability, right? If discrete logarithm problem doesn't hold, but we're assuming it does. So we go through here and just kind of making more explicit some of the assumptions here. If alpha was chosen randomly by the prover, then R is randomly distributed, and K is going to be information theoretically secure within R. Again, you can manipulate this by solving the discrete logarithm problem, but we assume that you can't. And it's also worth noting that if the prover reuses alpha to prove his knowledge of that private key, anybody who knows both challenges is going to be able to compute K. They just essentially, it's a process of elimination. You got two equations with two unknowns, so you slam it together and you can compute the private key based off of the set of responses and challenges. So it is very important to know that if you would like to use a Schnoor signature, that you do not reuse alpha for two sets or two iterations of doing that. And here we have just a straightforward implementation of the Schnoor signature itself. So again, you can just step through this process. This is exactly the same steps described here. You get 1, 2, 3, 4. And here, you're starting with a, oh boy, private public key pair. You go through the process, step 1, you generate that random alpha and then provide alpha g to the world. The verifier generates their challenge, the prover generates their response, and V performs the computation and checks that R equals R prime and verifies that. So let's just run the code quickly for a demonstration. There we see the verified output, so that worked. But if we imagine, again, if you reuse alpha for two different iterations of this process, and that's what we're imagining ourselves doing here. And let me scroll down to this process. So let's imagine that the verifier sends another challenge, and the prover generates another response with that same alpha. And so we've got now this challenge prime and the response prime that we're imagining. And here you see, this is as it fits into the 0 to Monero text. With that, we have this nice little formula for k. Let's compute the numerator, let's compute the denominator, and we just pump through the solution. And if indeed we have identified the private key with this solution that we figured out, then oh no, other people have discovered our private key. And sure enough, we run this code and we can see, yep, we verified the initial Schnoor signature. And oh no, you have now leaked that private key by reusing your alpha and sending it through. So there's that. Okay. So finally, what we want to note about this process, and they actually noted it right here at the beginning, right? It's an interactive authentication protocol. In terms of, both people actually have to, or both participants are actively making moves. This sort of leaks in that if the prover knew the challenge from the beginning, which is to say, if the verifier and the prover conspired such that the knowledge was sort of prearranged, then the prover would be able to generate a random response R, compute alpha G off of it, and when they actually send R to the verifier, they would be able to prove knowledge of the private key without having to know it, right? So bottom line, if the prover and verifier are conspiring, then just someone who's observing this process from the outside, an outside observer would see events or see this, process proceed through the steps 1, 2, 3, 4, and they would think, oh yeah, this has been verified, when in fact that is not the case because they've just conspired. And therefore, it's worth noting that this scheme is not publicly verifiable. So we note, as a challenger, the verifier is just spitting out a random number. That's what we're talking about here, where the verifier is generating this random challenge C that exists in the field we're interested in. But if you think about it, then the verifier in a non-interactive way could potentially generate a random number. And in that fashion, we have these hash functions that we've discussed a little bit so far. But if we're interested in a random function that we're going to insert to just sort of auto-generate a challenge, we can do that with a hash function. And that's sort of the next step in this process, right? Using a hash function instead of the verifier to generate the challenge. And when you do that, that is the process that is known as the Fiat-Shamir transform, and it makes this interactive proof non-interactive and publicly verifiable, right? Now it's just the prover is going to go through this sequence. There's no possible, conspiracy that they could have between themselves and the verifier, and therefore this becomes a non-interactive process where the prover just goes through and it's publicly verifiable because there's no conspiracy. All right, so with that established, we now are given this non-interactive proof version, this Fiat-Shamir transform, where we start very similarly, right? Again, this is just the prover going through this process here. So the prover is going to generate the random number alpha that exists in the field we're interested in, compute alpha G, and then they compute the challenge themselves using a cryptographically secure hash function. So you get the challenge, which is just the hash of alpha G, and then they can define the response to that now with this challenge, as well as with the challenge times their private key, and you add alpha to that, so you now have this response, and you can just publish the pair of information that you've calculated here, which is alpha G and the response. And once someone has gone through that process and published this proof pair, now someone can come in later as a verifier and calculate a different challenge C prime, which is the hash of alpha G, right? And keep in mind, this should be the same thing that the prover did in step 2. Now they're just going to calculate C prime. And then they calculate this other response, right? They take R from the proof pair, and they multiply that by G, and they compute R. And now you have everything that you need to calculate R and R prime here. You get alpha G published from the proof pair itself, along with the C prime challenge you calculate in step 1, and then the public key, which obviously is publicly published information in this scheme. And again, we're checking that the R equals R prime, and that if that is the case, then the prover must know the private key K. And again, we note, if the discrete logarithm problem is broken, then this doesn't hold, but that is the case. So I guess just quickly looking through this process, like you say, if RG is calculated, the scalar product of the value R and G, right, that response, that is the same, or that is mathematically equivalent to this little equation here, right? That was how it was originally generated. So this times G is the same thing as this times G. And since we know that, this is just directly how we calculate the capital R, that first point, response point, I guess, this person can take this alternate path to go through that calculation, whereas here you have the private key rather included. You switch that up to involve the public key, and then you can calculate the point R prime, and then check their equivalence. So just to go to the code example of it, here, let me get rid of the Schnoor signature section here. Got the Fiat-Shamir transform. And again, we're just stepping through the process. You start with a private public key pair, and you generate. You know what? I'm not going to walk through it this time, but you can see, again, we're just following through. You publish this proof that has this proof pair, I should say, which is alpha G and the response value R. And then, the verifier can just go through, calculate it all up, check that they're equivalent, and if that's the case, we'll get this nice little prompt, publicly verified P knows K. And you run that code, there's the response. So this goes on to talk about the resources that are required to perform this verification process. Ideally this would be just computationally absolutely trivial. But we're going to note, hey, how much data do you actually have to have on hand in order to handle a proof, and how much time, how much computational effort does it take to actually go through that process? We note that this scheme allows you to store a single elliptic curve point, right? Alpha G is in fact a point, and one integer value, which is just this response value, that lowercase r, again, integer value. So you can store those, and then whoever has published their public key, which again, public keys are elliptic curve points, that's all the information to sort of set things up for this. It's noted, since hash functions are pretty fast to compute, that this verification process is mainly a function of the elliptic curve operations. Handling the elliptic curve points, manipulating them, that's what really requires some horsepower to go through. Okay. So moving on to signing messages. One sec. So a signature is performed on a cryptographic hash of a message rather than the message itself in most cases, right? If you're going to sign something, it would be really easy just to sign the hash of the message rather than figure out a scheme to take in the entirety of the message and whatever length and all the rest of it. So yeah, and it mentions, this is just about signing messages of varying size in a consistent manner. Talks about how we're going to loosely use the term message and the symbol for it that is being used, this italicized M, to refer to the message, properly speaking, and or its hash value, so one or the other. As we go through this, just know when you see M, that means the message or its representation in the process. So we're talking about, signing messages is a very common procedure in terms of internet security. You want someone who views a message to be confident that it was actually authored, and that it was actually authored by the person who's saying it was authored by them. And for that, we're going to, I guess, dive into this signature scheme. Um, one common one being ECDSA. I won't pretend to be an expert on these things, but anyway, fun notes. So we're about to look at a signature scheme that is an alternative formulation of the transformed Schnoor proof from before, right? So this Fiat-Shamir transform, where we're making it non-interactive and publicly verifiable, we're going to set up a signature scheme that's based off of that. And it's we want to keep in the back of our mind that as we're looking at this signature scheme, we want to keep in mind this is a stepping stone for exploring the ring signatures in the next chapter. So with that, we have the process for the signature itself. Again, starting with a private public key pair, and to unequivocally sign an arbitrary message M, you go through the process. And this should look familiar, right? Very similar. We're starting by generating a random number alpha that exists on the field. You compute alpha G. You calculate a challenge based on the hash of the message and alpha G. So in this case, I think we're just inserting this message into the challenge production from the Fiat-Shamir transform. And then define the response R so that alpha equals R plus C times the private key. Or, in order to calculate R, is you just set alpha minus that same term. And then you publish your signature, which includes the challenge and response. So now any third party who knows, the general setup that you're using, right, which elliptic curve and your generator point and all of that, and all of that should be, standardized for whatever you're publishing and dealing with. But anybody who's familiar with that and has the signature and the hash function that you use to do this, they can, along with the public key, yes, of course, they can verify the signature. So you've got all of this information as a verifier that is just publicly available, along with the signature that was just published, and you can go through, calculate a challenge C prime equal to the hash of the message plus this term. And keep in mind, the point of this is that this term, RG plus C times the public key K sub A, what that ends up doing is creating an equivalent to that original challenge, right? So we just calculate that, test it against the original, and make sure that they're equal. And yeah, finally, and again, we're always mindful of how much data has to be stored. In this case, we're storing 2 scalars and need 1 public key. So the actual signature is 2 scalars, and then of course you're actually checking a public key, which everybody needs to know. So they go through the process, again, just explaining the original challenge and C prime are the exact same thing. And so, yeah, when you test their equality, that's the verification. Just a quick run through here. You just have that process along with this simple little print where we're checking C equals C prime at the end. And, if it works, we should just see a nice little prompt, signature passes, and indeed we do. And right, like you say, as you would want from any signed message, at the end of this process, we know that the owner who created the message has signed it, and that this message was not formed, unless the discrete logarithm problem is broken. This was not forged, and a verifier can be confident that that is the actual message, that it was created by Alice, that it has not been modified. All right, that does it. So thank you for your attention, and I hope you learned something.